Marhaba. Okay, in this session we want to start talking about a new field in mathematics called combinatorics. So combinatorics, one can say it is the art of counting. So all what we will do in this chapter is learn counting techniques. We want to learn how to count, how many ways we can accomplish a task. Okay, or how many ways there are to perform a mission, and how many objects of such properties there are. So all what we want to do is just count the number of different ways there are. So the first technique we want to learn in combinatorics is called the product rule. Okay, so let me say what is the product rule. So it says that suppose we are asked to perform a mission which can be broken down into a sequence of two tasks. So we are asked to do any mission you want, and this mission can be broken down into a sequence of two tasks, say. So first you do task 1 and then you do task 2. And to accomplish task 1, there are many ways to do it. You choose one of them and any one of them will do the job. So to do task 1, there are many ways. And to do task 2, there are n many ways. Once we do task 1 and task 2, we will accomplish the mission. And the product rule says that to accomplish the mission, we have m times n many ways to finalize the mission. Okay, so let me say the product rule again. We have a mission. We break it down into two tasks. So into tasks, for simplicity, suppose we have only two tasks, task 1 and task 2, and task 1 can be accomplished in m many ways, task 2 can be accomplished in n many ways, then the whole mission can be accomplished in m times n many ways, the product of m and n. Okay, so let's have many examples applying the product rule. Okay, so the first example. Okay, suppose we have 12 available offices. We are in a company and we have 12 free offices, and suddenly we have two new employees called Fadwa and Nizar. And we want to assign to Fadwa and Nizar different offices. So in how many ways we can assign Fadwa and Nizar different offices? Okay, so what is our mission? Our mission is to assign one office for Fadwa and one office for Nizar. So now we want to think about how can we break down this mission into smaller tasks. So the first task, okay, so task number 1, we want to assign an office to Fadwa. Office, okay. So we assign an office for Fadwa. Okay, and what is task 2? Again, we assign an office for Nizar. And now we want to see in how many ways we can accomplish each task. Okay, so look, we have 12 offices, available offices. We can choose any one of them and give it to Fadwa. So here, okay, so here we have 12 ways to assign an office to Fadwa. We just choose any of the offices and give it to Fadwa. Now, in how many ways we can assign an office to Nizar? We have only 11 ways. Why? Because among the 12 offices, available offices, we chose one and give it to Fadwa, and now what is remaining is 11 offices, which we can choose one of them and give it to Nizar. So overall, so there are m times n, so 12 times 11 ways, and this is 132 ways, okay, to assign, 132 ways to assign offices to Fadwa and Nizar. Okay, and so this is how we applied the product rule to solve this problem. See, there are a huge number. So maybe say the 12 offices are numbered office 1, office 2, office 3 anyway. So maybe we can give Fadwa office number 7 and Nizar office number 11. But there are 132 ways, different ways to give 2 offices to Fadwa and Nizar. Okay, let's see another question. Okay, how many words are there whose first part is an uppercase English letter followed by a positive integer not exceeding 10? What does it mean to be positive integer? So positive integer, it starts from 1, 2, 3 up to 10, and we should not exceed 10. So from 1 to 10. So examples, let's have examples of such words. The first part is an uppercase English letter. So we can start with the letter D and then here put 7. So we are talking about such examples. So D7 or Z2 or A9 or E4 and so on. So how many such words there are? So you can see that we can to form such a word. So this is our mission, to form such a word. There are 2 tasks to do. The first task, so here task number 1, choose an English letter, uppercase English letter, and then once we choose it, so like here, so we chose D. Now what's next is to choose a positive integer less than or equal to 10, right? So task 2, we choose a positive integer less than or equal to 10. Okay, now let's see how many ways are there to choose an English letter. Okay, so we know there are 26 English letters from A to Z. So there are 26 ways to choose an English letter. And now how many ways there are to choose a positive integer less or equal to 10? We have 10 choices from 1. So here what are the choices? 1, 2, 3, up to 10. We have 10 choices. So here in step 2, we have 10 ways. Okay, just let me... Okay, so here we have 10 ways. So what this means that, okay, this means that how many ways are there to form such a word? It's m times n. Okay, so there are 26 times 10, which is 260 such words. Okay, so there are 260 words where the first part is an English letter and the second part is an integer positive integer not exceeding 10. Okay. Now let's see another question. How many binary strings of length 5 are there? Okay, so for example, let's have some examples of such binary strings of length 5. So for example, 1, 0, 1, 0, 1. This is a binary string. So binary means using the digits 0 and 1. And here of length 5, we have 5 digits. Another example is 0, 0, 0, 1, 0. Another example is 1, 0, 1, 1, 1, and so on. How many of these are? So you can see that this problem can be divided or broken down into 5 tasks. So we have 5 tasks. Let me tell you what are the 5 tasks. The 5 tasks is to fill the 5 digits. So task 1, fill digit 1, fill digit 2, digit 3, digit 4, and digit 5. So these are the tasks. So this is task 1, task 2, task 3, task 4, and task 5. Okay, so these are the tasks. Now, in how many ways we can accomplish task 1, which is what? To fill the first digit. And to fill the first digit, we have either 0 or 1 to fill it. So here we have two ways to fill task 1. Now, in how many ways we can accomplish task 2? Again, we have 2 ways. Either we choose 0 or 1 to fill digit 2. And the same for task 3, the same for task 4, and finally task 5, we need to fill the 5th digit, and to fill it, we only have 2 ways to visit, either choose 0 or choose 1. Okay, now the product rule here is composed of 5 tasks, and we multiply the number of ways of all the tasks together. So this is 2 times 2 times 2 times 2, we get 2 to the power 5, which is 32 binary strings of length 5 we have. Of length 5. Okay. So this is the solution, the answer of this question. How many binary strings of length 5 are there? There are 32 binary strings of length 5. Okay. Let's take an example from Egypt. So how many different car plates are there in Egypt? Knowing that a car plate is made from a sequence of 3 Arabic letters followed by 3 decimal digits, right? For example, okay, one example of a car plate is we need to choose 3 Arabic letters, say Mim, Sad, Ra, and we need to, which will be followed by 3 decimal digits. So we can say 8, 4, and 1. Okay, this is an example of a car plate in Egypt. And the question is how many such car plates there are. We see that there are 6 tasks to form one car plate. What are the 6 tasks? So this is task 1, task 2, task 3. What is task 1? Choose a decimal digit from 0 up to 9. And task 4, choose an Arabic letter. Okay, task 5, choose another Arabic letter. And task 6, choose another Arabic letter. So let's see, to accomplish task 1, we have how many ways? We have 10 ways. From 0 to 9. We can choose any digit from 0 to 9. Similarly for task 2, similarly for task 3. And now to choose task number 4, we need to choose one Arabic letter, and we have 28 such letters, and similarly for task 5 and similarly for task 6. Okay, when you compute this number, you find that it's a huge number, but maybe not huge for Egypt, and the number will be 21,952,000 car plates. So at some time in the future, all of these car plates, all of these codes will be used. Okay, so this is the maximum number of plates of this form. Okay, now let's have another question where we want to use the product rule. Let A and B be sets where the cardinality of A is M and the cardinality of B is N. So A has M elements, many elements, and B has N many elements. The question is, how many different functions from A to B are there? Okay, remember, what is a function? A function is an assignment. A function from A to B is an assignment which assigns to every element in A one and only one element in B. Okay, so let me draw a picture. So A here is the domain of the function, and B is the codomain of the function, And in A, we have how many elements? M elements. Let's call them A1, A2, up to AM. And in B, we have N elements. Let's call them B1, B2, B3, up to Bn. And we want to look at how many different functions from A to B. So let's see, how can we construct a function? What is a function? It's an assignment which assigns to every element in A some element and only one element in B. So we can to construct a function. Let's break the construction of a function into several steps. So to construct a function from A to B, we do several steps. Okay, the first step. Okay, what is the first step? Look, a function has to assign an image to every element in the domain. So step 1, assign an image to the first element. So assign, so if you want assign, okay, assign an image for the first element in the domain, A1. Okay, say we assigned B3 to be the image of A1. Now what's step 2? Is assign an image to the second element in the domain for A2. Okay, let's assign an image for A2. Then it could be B1. B1 is the image of A2. Now step 3, assign an image for the third element in the domain. It's A3. Okay, say this is A3, and now we want to assign an image to A3, but we can choose B3 to be also the image of A3, right? Okay, so that's valid. We assigned B3 to be the image of both A1 and A3, and so on. So we keep doing this until we reach the mth step, right? Because we want the last element in the domain is AM, and here we need to assign an image for AM. And once we assign an image for the last element in the domain, we have a function, because we assign to every element in the domain one image. To each element in the domain, one image. Now let's figure out how many ways there are to accomplish the first tasks. In how many ways we can assign an image for A1? So the image of A1 could be B1 or B2 or B3 up to Bn. Anyone in the codomain could be the image of A1. And the codomain has n many elements. So here we have n ways to define an image for A1. Now let's look at A2. Here is A2. What could be the image of A2? It could be B1 or B2 or B3 up to Bn. Again, any element in the codomain can be the image of A2. So here we also have n ways. Okay, let's see how many ways we have to define an image for A3. Similarly, A3 can have an image of B1 or B2 or B3 up to Bn. Also, any element in the codomain can be the image of A3. So here we also have n ways, and so on, all the ways. Every element in the domain has n many ways to assign its image. Okay, so now how many functions do we have? We have n times n times n. How many times? M times. Okay, so there are n to the power m many functions from A to B. Okay, you see why? Because again, maybe you can see, maybe I can say it again quickly here. So here is A1, here is A2, here is A3. These are the elements of the domain. Okay, sorry, we have m many elements in the domain, And to assign an image for A1, we have n ways. To assign an image for the second element in the domain, we have n ways. To assign an image for the third element, there are n ways, and so on. So in total, there are n times n times n, m times. And so this is n to the m. Okay. Now let's have another question. Similar, but also we are talking about functions. Again, A has m elements, the domain has m elements, the codomain has n elements, but we want how many injective functions. Okay, let's see. Suppose here is the domain and here is the codomain, and say we assign A1, let's say for simplicity to B1. Okay, now let's look. What could be the image of A2? It could be any of the elements. So here we have B2, B3 up to Bn. Okay, it could be any element in the codomain except B1. You see why? Because if we assign B1 to be the image of A2, then we will violate injectivity. Two elements will have the same image, and this means that the function is not injective, but we are looking to the number of how many injective functions are there. So the image of A2 can be anyone except the image of A1. So maybe the image of A2 is B3. That's fine. Now let's look what could be the image of A3. It could be any element in the codomain except the image of A1 and the image of A2. So it could be Bn, for example. So how many ways we have to assign an image for A3? All the elements in the codomain except B1 and B3. So except two choices. So again, let's say to form a function, we need to assign an image for A1 and assign an image for A2 and assign an image for A3 up to the last element in the domain, and we have m elements in the domain. Okay, so now let's see how many ways we have to assign an image for the first element. We can choose any element in the domain, in the codomain, and here we have any elements in the codomain. Okay, remember here we have cardinality of A is m and the cardinality of B is n. Okay, now we chose an image for A1. How many ways we can choose an image for A2? We can choose any element in the codomain except the image of A1. So this leaves out n minus 1 choices. And now in how many ways we can choose an image for A3? We can choose any element in the codomain except the images of A1 and A2. So here we have n minus 2 choices. And so on. So let's see what is the number of ways to assign an image for the last one in the domain, this one, AM. Okay, it is all the choice. We can choose any element in the codomain except the images of the previous ones. And how many previous ones here we have? So here, how many elements before AM there are? We have m minus 1 elements. So we have n elements in the codomain, and we should disregard the images of the previous ones, which are m minus 1 many. So this is n minus m plus 1. So there are this number of ways to choose, this number of available elements in the codomain to choose from as the image of AM. So this will be n minus m plus 1. Okay, so there are n times n minus 1 times n minus 2 up to n times m plus 1 many. Now we multiply the number of ways of each task, okay, by the product rule, many injective functions. Okay, let's take a specific example. So suppose the domain of the function has 3 elements. Let's say the 3 elements are A, B, and C, and the codomain has 5 elements. Let's say 1, 2, 3, 4, and 5. So this is A, and this is the codomain B. Then how many functions are there from A to B? Again, A has 5 choices. The image of A can be any element of B, similarly for B, and similarly for C. So there are 5 times 5 times 5. We have, remember, n to the m. So we have 5 cubed, which is 125 many functions from A to B. Okay, and how many injective functions are there? So to choose an image for A, we have 5 choices, namely 1 or 2 or 3 or 4 or 5. To choose an image for B, we have any element from here except the image of A. So we are left with 4 choices. And now to choose from C, so suppose the image of A is 2, the image of B is 4. Now, to choose an image for C, we can choose either 1 or 3 or 5. Any of the left, any number which is not the image of the previous ones. So here we have 3 choices for C, and this means we have 60 many injective functions. Okay. Of course, we expect the number of injective functions to be less than the number of all functions. So here we have 60 and here we have 125 many functions. Okay, let's have our last example in this about the applications of product rule. What is the cardinality of the Cartesian product of n many sets? So suppose we have the sets A1, A2, up to AN. So these are sets. And we want to find the cardinality of the Cartesian product A1 cross A2 cross again up to AN. So we want to find out how many elements, and suppose all of them are finite, okay? These are finite sets. We want to find how many elements are there in this set. So in other words, how we will apply the product rule. Think of the mission is as forming an element of this set. Remember, what is this set? A1 cross A2 cross AN. By definition, this is the set of all n tuples, so of all A1 ordered sequences of n elements, so from A1 up to AN, such that each AI belongs to AI. So this element belongs to the first set, and this second element of the tuple belongs to this set. Remember, a tuple is an ordered structure whose first element is A1, and A1 belongs to the set A1, and so on. And this one belongs to the last set. Okay, so we will use the product rule to see in how many ways we can form such an n-tuple. So to find the cardinality of the Cartesian product, the question boils down to how many n-tuples, such n-tuples, by how many such n-tuples are there. Okay, so let's think, how do we form such an n-tuple? Let's break it into steps. So task 1 is choose A1. Remember, we want to form an n-tuple, and n-tuple has this form, And to form it, we need first task. The first step is to choose A1. Second task is choose A2. And third task, again, choose A3. Okay, what is A3? It's the third element in the tuple. Remember, this is the tuple. We are forming a structure of this form, and we will finish constructing this tuple when we choose the nth element. So choose AN, where AN is the last element in the tuple. Now let's see in how many ways we can accomplish task 1, which means in how many ways we can choose A1. But what do we know about A1? A1 must be an element of A1, of the set A1. So here we can choose any element in A1. So this means that there are the cardinality of A1 ways there are. So look at the cardinality of A1 is how many elements in A1, we can choose any one of them. And similarly, to choose A2, we have the cardinality of A2 ways, because A2 must belong to the set A2, and so on, up to the cardinality of AN ways. And now, by the product rule, we just multiply these numbers. Okay. So multiply this number. So the total number of n tuples which have this property, that the first element is in the first set, the second element is in the second set, and so on, is the product of these numbers. And the total number is the cardinality of the Cartesian product. So the cardinality of the Cartesian product, what is the cardinality of the Cartesian product? It is the total number of elements in this set. And what are the elements in this set? Are the tuples of this form which satisfy the property that A1 is in the first set, A2 is in the second set. And we've seen there are this many ways: the cardinality of A1 times the cardinality of A2 times the cardinality of the last set. This is the total number of ways to accomplish the mission. And what was the mission? Forming this tuple. Okay. So we use the product rule to prove what we have seen before, that the cardinality of a Cartesian product is equal to the product of the cardinalities of the sets in the Cartesian product. Okay.